Right, so now it's time for us to have a look at a theorem dealing with vector fields in 3 space. And this is in particular going to be a divergence theorem. So far we've been looking at vector fields that are planar, so only have x and y components. And we've seen that with Green's theorem we can link together kind of the macroscopic circulation of our vector field with the microscopic by summing over the whole region. And right at the end of the previous lecture we discussed an alternative, which is a divergence theorem in the plane, which also looks at the kind of macroscopic divergence, so just thinking around a circular path, how much divergence is there, and comparing that with summing over the entire region, all the little divergences. So it might be an obvious question to ask, supposing we have a field in 3 dimensions, are there similar theorems that we could use? And the answer is yes, and in fact there are quite a few. The particular one that we're going to have a look at is, well, some people call it the divergence theorem, particularly if you're in physics and electromagnetic theory, you'll be hearing about Gauss's theorem. What does it say? Well, it looks very similar to our divergence theorem that we've seen in the plane. It says that if you have a look at the divergence of our, now remember this is a 3-dimensional vector field, so this is our f has an x component and a y component and a z component. So if we have a look at the divergence of that, so remember the divergence measures how much our field kind of is emitted from a point, or how much it expands or contracts. So we look at the divergence over the whole domain. So here we're thinking about the divergence over a volume. So we're thinking about how much the field expands over a volume. That's going to be the same as if we look at, well, we're going to look at just the surface of our volume, and we're going to see how much, if we think about what this means over here, this takes our vector field, whatever it's doing, and dots it with the normal, so it sees how much of the vector field is pointing out of that surface, and it adds up all of that. So again we have a kind of macroscopic microscopic thing. So on the right hand side over here we could think about having some 3-dimensional shape, and we're kind of adding up how much of the field kind of points out of that. So it's a kind of macroscopic divergence. And if we think about what we're doing over here, we're looking inside our shape at each possible point within there and thinking about each possible little divergence. We're adding all of those up throughout the entire volume. And what Gauss's theorem says is that if you add up all these little microscopic divergences in the volume, it's going to be equal to looking at the kind of macroscopic, what we'll call a kind of macroscopic divergence around the surface. So very similar in the look and feel to the divergence theorem that we had in the previous video. Again, although there is kind of physical significance to this, a lot of the time these theorems get used just to make life easier. So let's have a look at an example. So we're going to take as our vector field this bunny over here. So we can see it's got an x, y, and z component. And the surface that we're interested in is the closed surface bounded by the solid cylinder R, defined by x squared plus y squared is less than or equal to a squared. And the thing that we want to do is we want to find the surface integral of vector field on this surface. So for this one we're actually going to use cylindrical coordinates. So I thought this would be a good chance to bring in cylindrical coordinates if you haven't seen them before. So the idea is sometimes you want to work with a cylinder, and it can be useful to have specific coordinates for that. They should look quite familiar. So we have, if we've got some point P, how are we going to identify it? Well, it's in 3 space, so we need 3 coordinates. We're going to look at, from the x-axis, we're going to measure the angle to the line which we get if we drop a perpendicular down from that point onto the xy plane. So we're going to have a radius and an angle, which is a lot like our polar. So it's basically taking our polar coordinates, so that's just straight polar. And then because we're always going to be, well, we're usually going to be somewhere in the z direction as well, we're just going to add the z coordinate. So we have an r and a theta that are the same as our polar coordinates, and then we have whatever our z component is as well. If you want to think about the coordinate surfaces for our cylindrical coordinates, we've got our r, which is really just how far, so our r coordinate here is how wide the cylinder is. If we're thinking about our z, we're thinking about this, and if we're thinking about theta, we're thinking about the angle like so. So you can go and have a look at that. Whenever we're dealing with a new coordinate system, we also need to think about what is the area element and what's the volume area element. For cylindrical coordinates, we have these two. So our area is r d theta dz, and our volume is r dr d theta dz. Here's a picture from the internet which also shows alternative notation that often gets used for cylindrical coordinates. So you'll notice here they're using a rho, which in the textbook, our textbook is an r, but often for cylindrical, just to kind of indicate that we're using cylindrical rather than spherical, we'll use a rho for the radial, and they'll use a phi, whereas in our textbook, the textbook is using theta. And so this little image over there gives you the area element and the volume element. Okay, so we're going to use that to solve this question. So let's go back to it. Here's our field, and we want to have it, and we want to measure the flux through the surface, where the surface is this solid cylinder. So let's sketch that cylinder, just so that we have a picture in our head of what it is that we're doing. Okay, so here's an x, y, and a z. What does our cylinder do? So the radius of the cylinder has to be less than a squared, and we're centered around the z-axis, and our height of our cylinder is going from 0 to b. So we've got a cylinder doing roughly something, something like this. So it's sitting on the xy plane, so it's going from 0 up to a height of b, and it has a radius of a. Alright, well, if we were to write this all out, it would look a little bit hairy if we were to write out our surface integral of f dot ds. Then we'd have this whole thing over here dotted with ds, whatever our ds element is. But with joy and delight, we remember that we have Gauss's theorem, so in fact we can turn this into a divergence theorem. So we have this is equal to, we're just going to integrate over the entire region instead of just over the boundary surface. So now we're integrating over there, our divergence of f. And hopefully that's going to look a little bit better. Let's calculate our divergence. Well, our divergence is the dot product of our nabla with f. So, and that's df1 by dx plus df2 by dy plus df3 by dz. Here we have f1, here's f2, and here's f3. So taking those derivatives, I want the derivative of f1 with respect to x, so that's going to give me a by squared. If I take the derivative of f2 with respect to y, it's going to give me x squared. And if we look at df3 with respect to z, that's going to give me 2z x squared plus y squared. And we can do a little bit of rearranging here. Notice we've got an x squared plus y squared here and here. We can take out some common terms, and we've got a b plus 2z times x squared plus y squared. So that is our div f, our divergence of f. So that looks like quite a nice thing to integrate. So what we're actually wanting to do is say, well, our double integral, which is the thing we were originally asked to find, is going to be the integral over our region of x squared plus y squared b plus 2z dv. And this is the point where it becomes useful to use cylindrical coordinates. Obviously you don't have to, but they make life easier. So we've got our dv, we know that that's this thing over here. So we're going to have x squared plus y squared. Oh no, we're not, because the thing to remember with cylindrical coordinates is that, again, just like in polar coordinates, we have x squared plus y squared is equal to r squared. So what we end up, so this becomes an r squared. In cylindrical, we keep the z, so this term is going to stay the same. So we've got the integral of r squared b plus 2z, and we need our volume element, so that's an r dr d theta dz, and we need to think about our limits for our integration. Our dr, well, let's make this in green. Our r is going to be from 0 to a, so that'll be from 0 to a. If we think about our d theta, theta measures from the x-axis around like our polar coordinates, so our theta is going to be from 0 to 2 pi. And finally our dz, we're measuring from 0 up to b, so that's going to be from 0 to b. And there we go, straightforward integral. You can go through and work out the details, step through it, and you should find pi a to the 4 b squared. So again, if you compare what we would have had to integrate if we'd done this, if we'd worked out the surface integral, we would have worked with this whole vector field here dotted with ds. So remember, that is kind of the surface vector, normal vector, dotting with our f, and we'd have to do the whole surface integral, which would have been kind of complicated, but in fact we ended up just doing a nice little volume integral. Okay, so that is our first example of why Gauss's theorem might be delightful. Let's have a look at another use of our divergence theorem. So let me grab my notes. Okay, so we would like to evaluate this integral, or this scalar field over that surface. And you might initially think, but that doesn't look anything like Gauss's theorem, but we can in fact turn it into something that looks like Gauss's theorem. So what we want to do, so to use Gauss, we need to have some vector field, because if you look at what Gauss's theorem says, we need to turn the scalar field that we had into some f dot n. So that's what we want to do. So what we're looking for is we want to turn this thing into some surface integral of an f dot ds, because then we can use that. I've got my dot n, and we can translate that into a divergence, which we can integrate easily over the whole volume. So I have written that technically correctly. The way we've seen it is okay. So we need several things. We need this normal, and we need this force over here. So we are a sphere of radius a centered at the origin. So let's have a look at that. So here's my coordinate axes, and let's draw our sphere. So we do something, oops, got something like this going on. Okay, and we've got a radius of a. So the first thing we want to think about is the normal, and we want to have the normal pointing out. So we want our normal, our unit normal, to be something like that. Well, how could we find that? Well, at any point that we're interested in, we know that our radial, if we're thinking in spherical coordinates, our radius, our point will point out, our radial vector. So our normal, just any old normal, would be, our normal at any point on the surface would just be our position vector. If we want that to be a unit normal, we can just divide through by the radius of the cylinder, of the sphere. So let's just put that in x, y, and z. That's going to be, so that's our r, and we're dividing that by a. Okay, so we've got that bit. Now we want an f vector field, so that when we dot it with this thing over here, we're going to get x squared plus y squared. So you can play around a little bit, but it turns out that the f that we want is, let's have a look, what should it be? Okay, so you might be able to find other x's, other f's that do this, but if you just check, we want to make sure that del dot f, so we want to check that the divergence is equal to this thing over here. Well, we want, so our divergence says take the x derivative of the x component, so that's just going to give us, let's just check, that's going to give us an a, and we're going to add it to the y component, partial derivative with respect to y, so that's just a times y with taking the derivative with respect to y. It's going to give us an a, so that's 2a. Okay. And how does that help us? Oh, I just calculated the wrong thing. We're going to need this in a moment. But to check that this was the actual f that we wanted, we should have checked that f dot n gives us this. I was silly. We want to check that f dot n is equal to x squared plus y squared. If we dot that, so we've got our axi plus ayj, and we're going to dot that with our n, and you can calculate, so our n is this thing over here, and you'll see that you do end up with x squared plus y squared. So that's nice. Okay, so now that we've shown that we've found an f so that we can write things, we can use our divergence theorem. So we've written our x squared plus y squared ds is equal to our f, which is a xi plus yj, dotted with our n, so that's our xi plus yj plus zk all over a, so a's cancel. Pure, which is looking kind of hectic, but because we have our delightful divergence theorem, we can now say, well, actually, if we just take the divergence of f, which I just found, and integrate over the volume, we'll be done. So this must be equal to our div f over the volume. So I found div f over here when I wasn't concentrating. So we've got our integral of our volume of 2a dv, and am I right? Yes. Okay, so I'm going to let B be the ball that is bounded by the surface that we've got. So our surface S is just the surface of the sphere. I'm letting ball be the whole thing. B be the whole ball, the whole solid thing. Then what we've got over here is the thing that we're trying to find. Is in fact equal to the integral over our ball of this thing here. But this is just a constant, so in fact that can come out. It's 2a, and so we've got the integral over the ball of just the volume. So all we want is the volume of that sphere, but we know what the volume of a sphere of radius a is. So this is we know this from a long time ago, 4/3 pi a cubed. So plugging that all together, we end up with 8/3 pi a to the 4th. So although we've done quite a lot of thinking along here, it's probably still quicker and less work to have worked out this volume integral over here than it would have been to figure out the surface integral of this thing over the whole surface. You could certainly do it, and I encourage you to try, but Gauss's theorem makes things much quicker. So one of the other ways in which Gauss's theorem gets used is to solve tricksy problems that will come up in particularly electromagnetics, and if you're doing relativity and things, which you might not be able to solve using other techniques. So let's have a look at an example. Okay, so we've got some irregular, some regular domain, so a reasonable shape in 3 space, and we're thinking of S as the surface of that. So something like this shape here that's been drawn in 3 space. The only thing we're assuming is that the origin is somewhere inside this space, this shape that we've got. And what we'd like to do is we're looking at this vector field, which we've seen quite a lot before. So it's the it's the vector field of, for example, a point mass that is emitting charge or something like that, or you can think about as a point mass that has gravity, anything like that. So we're thinking about the field, maybe the gravitational field of a point mass at the origin or something. And we want to find the overall flux of this out of the surface. So how much of this field is leaving the surface of this space. Okay. So what we've got is this thing here is the unit normal outward on S. So here it is shown over here. Okay, well, what can we do? Well, you might be tempted to immediately dive in and say, oh, let's use Gauss's theorem. But there is a problem here. So F needs to be a smooth vector field defined everywhere on D. But if we have a look here, our domain D contains the origin, and at the origin F is not defined. Okay, so what does that tell us? So we can't use Gauss immediately. We're going to have to be a little bit cunning. So this is one thing to check. If you're going to use any of the theorems that we've talked about so far, your vector field needs to be defined. And up until now, we haven't seen a case where it wasn't, but here's a very simple case. There's a point within the domain we're interested in where it's just not defined, so we can't use it. Okay. So what are we going to do? We're going to use a little trick. So we're going to start by imagining that we've got a little sphere around the origin, which we're calling S star. Okay, so S star is a small sphere contained within D. Okay, and it's centered at the origin. All right, so we can see that there. And the next thing is we're going to define this normal n star here as the normal pointing in. So this is the unit vector, so n star is our unit normal pointing into our little sphere, S star. Okay, and the next thing, the final thing that we're going to define is we're thinking about all the regions within D, but not in that little sphere that we've got. So that's going to be D star. So we've got D star, which is the part of our overall space outside our S star. Okay. So one of the things that you can check for yourself is that the divergence of our field is equal to 0 on D star. So the divergence, if in a region that doesn't include our little point source, is going to be 0. Okay, so this is, you can check that for homework. If you get stuck, you can also see example 3 in 16.1. Talks through it a little bit, but I recommend you can totally do this by yourself and you can check that. Okay, so we know that the divergence on D star is 0. What else do we know? Well, if we think about the flux going into, so we're thinking about the flux, if we look at our little ball, and we look at the surface integral on our little ball, then we can also show that that is equal to minus 4 pi m. again, check that for homework. It's pretty straightforward. If you want to think about it, you're thinking about having a point source here. You've got a little sphere around it. Your point source is emitting, if you like, m units at a given time, and so our flux is measured over the surface. So you can check that for homework. Okay, so this, let's just make a note here, is the flux of F inward. And it is negative, which is kind of correct, because we are thinking when we look at a field like this, it has flux that's pointing outwards, so if we measure the flux going inwards, we would expect that it would be negative, because actually it's going outwards. How does this help us? Well, now suddenly we can say 0 is equal to, we know because of our divergence here, if we look at the divergence of F dV on d star, then because of this bit over here, that must be equal to 0. But we can use our Gauss's theorem to say our divergence on this here must be equal to the surface integral of F nds. So we're now looking at our divergence over the volume and saying, because of Gauss's theorem, we're now treating, so let's just be clear here, we're looking at Gauss's theorem on d star, because d star has F always defined on it. D didn't, but d star does. So our divergence of F on d star must be equal to our surface integrals on d star. What are the surfaces? Well, the surfaces of d star are big S and also S star. So we need to have two integrals. Here's the surface integral on ds on S, and then we also need to have the surface integral of F dot n star ds, and that's integrating on S star. Okay, good so far. So because our d star has two surfaces, if you like, it's the kind of the outer one that was the surface of d, and also the little inner one created by the sphere that we're thinking of. But from over this bit, we know that this thing is equal to minus 4 pi m, and we know that this is equal to 0, so we've got 0 is equal to, and look at the cunning thing that we just did. A little bit of rearranging without actually calculating anything at all says that the surface integral that we wanted to find is equal to 4 pi m. So this is quite a cunning trick, and if you hang around in physics, you will see it done quite often when you want to work out something like the flux of a point mass, and that flux is not actually defined at the point where the point is. Then you need to do tricks like this. So spend some time working through this. There are two good things to do for homework here. The first one is show that the divergence of this field is 0 everywhere except at the origin. Then the second thing is to show that the flux is through this little sphere around the point that you're interested in is 4 pi m, or equivalently the flux in the inward direction is minus 4 pi m. So those are two things to show for homework, and then putting it all together using Gauss's theorem, we can finally answer the question that we wanted to at the beginning. Okay, so that's quite a lot. Do some examples, and the final two videos The next one will be on Stokes' theorem, which is another theorem which makes life easier for us. And then the final video will just pull everything together into Maxwell's equations. All right. I will probably put the last two videos up on Sunday. So just spend some time with everything that we've done so far over the next couple days, getting familiar with it.